Okay, welcome to this week's massive lecture because we have time. This lecture will be kind of a double lecture. So we're going to talk about the HGL and the EGL. And I suppose really in the title, I should type these things out, and really it should be this is the hydraulic grade line and the energy grade line. And they're usually kind of written as the HGL, EGL, although really, let's face it, as you'll come to understand, the EGL is kind of the more fundamental, and the HGL is it's important, but it's not the same thing. So we're going to construct the hydraulic grade line and the energy grade line for various fluid systems, and I want you to understand the physical meaning of these things, and that's really the most important thing that we're going to have in this whole thing. The other thing that I want to do, and I just have this in my notes, so I'm not really sure why I have this here yet, but just kind of make a note that the head loss due to an expansion. Okay, so that's H with a lowercase l, and an expansion is V1 minus V2 squared over 2G. A lot of times at an expansion, if it's expanding into something that's really, really, really large, then this V2, which will be the velocity on the other side of the expansion, will go to 0 a lot of times. Okay, so a lot of times this will be V1 squared over 2G. But in general, just kind of, record that because that may show up somewhere. I'm assuming that it will. Anyway, so what we want to be talking about here, I'm going to kind of zoom in a little bit, and I'm going to talk about it over here, and then we're going to talk about that big pipe that I drew, is I want to talk about the, kind of one way to think about this quantity that kind of shows up a lot, P on gamma plus Z plus V squared on 2G. Okay, and I want to think about this as if this is the total energy of the system. Okay, and it's a little bit wonky, right? Because this is energy, but the energy is expressed in terms of lengths. Like P over gamma is a length. Z is a length. V squared over 2G is a length, and we call these things heads. So typically, we think about this as total head, but right now I want you to think about this as total energy. And one of the things about energy is that energy cannot be created nor destroyed. But it can be transferred from one form to another. Okay, now this, I want to make a point here real quick before we keep going with this, is that this is true, okay? As long as we're not talking about atomic, nuclear physics, which, we're assuming there's no nuclear reactions in our pipe. Basically, the energy in the system is going to remain constant, except for a little bit of loss, but we'll talk about that in a second. So basically, this quantity is going to kind of remain constant. So, for example, if I have just a random pipe here, here's my random pipe. Okay, notice all of these energies here. Let's zoom back in. All of these are lengths. Okay, this is a length. Okay, that's a length. That's a length. Okay, which means they can be shown graphically as lengths. And this is one of the reasons why we like to do it this way. So, for example, Z's the easiest one. Okay, so elevation. So if I wanted to get the elevation at any point in this flow, like let's suppose I wanted it here, or here, or here, or here, or here, or just anywhere. Okay, you want the elevation. Well, how would you go about getting that? Well, that's pretty straightforward, right? We would step up to the plate. We would say, let me see if I can find a trusty straight edge. We could say, well, give me a datum, and let's use that datum, and let's measure Z. Okay, so I'm not going to do all of those points because we don't have all day. But let's just imagine I would just go and I'd say, okay, well, this is going to be my datum. Okay, so this is the datum. And now here's Z. Okay, so let's look at this point right here. Okay, that's Z at this point. Cool, right? What about right here? Oh, look, there's Z right there. Okay, and we could do that for any point in this entire flow. Okay. Now, what about P on gamma? What if I wanted P on... Oh, what? That is not what I want. Oh, it is what I wanted. Okay, what if I wanted... Okay, so Z, easy to see. What about P on gamma? What if I wanted to see P on gamma? Okay, well, the nice thing about P on gamma is if you remember, P on gamma is kind of, if we back it up, we can kind of think about it from the hydrostatic law. course, the problem is none of this is hydrostatic. But I could do this. I could say, well, what if I put a little tube right here and one right here? And I just said, well, you know what? Let's see what P on gamma is. So let's create a little pitot tube, or a little, excuse me, not a pitot tube, a piezometer. Let's create two of these. Okay. And what's going to happen? Well, the water is going to kind of rise in those tubes, or the fluid is going to rise in those tubes until it gets to a height commensurate with its pressure, right? So it's however high the pressure is going to push it. So maybe like over here, it's like right there, let's just say. Okay. And over here, let's imagine that, let's imagine that it rises to, I don't know, let's say here. Okay, so now we've got, these tubes are full of water. Okay, how much water? Well, that can be visualized by doing a kind of little line like this. Okay, that's P on gamma. Okay, because in a hydrostatic fluid, remember, if I wanted to know what the pressure is right here, I would say, what's the pressure right there? Oh, well, it's gamma H. Okay, so P equals gamma H. You rearrange that, you get P on gamma, okay? So the same thing happens over here. We would end up with P on gamma. Cool, right? All right, so then I'm going to erase that. So then now if we zoom in over here, we could zoom back in, and now we know, we've kind of got an idea of the P on gamma, okay? Now what about the V squared on 2G? How would we get that? Okay, now the question is, you've probably forgotten this because most of my students do, because we don't talk about it very much. We talk about it and then we kind of move on. Is to say, okay, well, what about, well, there is another type of pipe, right? We can also put in a pitot tube if we wanted, okay? And what the pitot tube is going to do is it is going to help me get at the velocity head. Okay, so this thing's going to rise higher. Okay, now how much higher is going to depend on the flow, but remember, so this thing's going to kind of be pointing into the flow. Okay, now we've got two of these, one at each spot. Okay, and let's make that go as vertically as we can. Okay, and so that's going to be turning into the flow like that. Okay, and so what that's going to do is that's going to create a stagnation, and I'm going to draw this in a different color. We'll make it green. Why not? And we'll have it go up, and it's going to be about right there, and we'll draw this one. It's about right there, more or less. Okay, so then like this. Okay, and so what that records is that records the pressure at this point right here, but that is a stagnation point. So it has been risen, or it has risen by this amount. It's relative to just the piezometer, but this amount right here, which is V squared on 2G. Okay, or right here, this amount right here is V squared on 2G. Okay, so cool. So what we have right here, if I zoom all the way in here, is I have P on gamma plus Z plus V squared on 2G. That's the total energy. So look, here's the total energy right here. Let's see, how would we do this? I guess we can go back to black. Okay, we've got Z, P on gamma, V squared on 2G, boom. Total energy, okay, or really total head. Now, if I can look at it, and I could draw it, and I could say, well, look, okay, if I've done a good job here, which I'm not saying that I have, there you go, okay? So notice, the total energy can neither be created nor destroyed, okay, but can be transferred from one form to another. So as we went from here to here, the Z increased. As we went from here to here, the pressure on gamma looks like it went down a little bit. And as we went from here to here, it looks like V squared on 2G went down. So basically the elevation increased and the other two decreased. Okay, but total energy remained the same. Okay, so this is this idea that we're kind of driving at. And now, and this is the last time that I'm going to do it like this. But this line right here, this would be called the energy grade line, because this is the total energy in the system. Grade line. And that's the total grade line, sorry. And that's the total amount of energy in the system. Okay, this line, which is going to be harder to see because it's not flat. Okay, This is the hydraulic grade line, the HGL, hydraulic grade line. Okay, and basically the hydraulic grade line is the energy grade line minus ignoring this V squared on 2G. So basically it is what we call, well, I guess the way I will do this is I will say that the energy grade line equals P on gamma plus Z plus V squared on 2G. The hydraulic grade line equals P on gamma plus Z. Okay, so that's kind of how we get at these two. Okay, now usually the energy grade line is not flat, and so that's the interesting thing. Because there's one type of energy that we've forgotten, or one source, or in this case actually a sink of energy. What is that sink? Okay, and that sink is friction. So I'm going to show you like a more realistic drawing of this. We're just going to kind of zoom down, and we're going to talk about a more realistic drawing of this. And then I'm going to go through a whole bunch of diagrams from a different textbook, and we're going to talk about them. We're going to discuss why the energy grade line is what it is, and why the hydraulic grade line is what it is. Okay, so the one thing that I want to note is because of friction, basically what you can expect is this energy grade line to always be kind of sloping downwards. Okay, just a little bit of downward slope. Okay, I'm drawing it as if it curves downwards, but it doesn't necessarily curve downwards. In fact, usually it doesn't. It can do some funny things. Okay, but in this class, it's not going to really do that much funny stuff. Usually, it's just going to be straight. But let's talk about like a more like a simpler system. So let's talk about. I've got a pipe here. Okay, here's a pipe. Okay, and we're going to imagine that this thing has a uniform cross-section, so not as poorly as I've just drawn it. We're going to draw it better. Okay, so it's got a uniform cross-section. Okay, here's a datum. And I want to think about these quantities. Okay, so we're looking at P on gamma plus Z plus V squared on 2G. Okay, so the first thing I want to do is Z. Well, Z's straightforward. Boom, here's my Z. Right, my Z at either end of this thing is the same. Right, it's going down to this datum. No matter where I choose, it's going to be the same. What about we're getting ahead of ourselves. Okay, we got excited, right? Let's not think about all this stuff, okay? It's not that the Z is wrong, but when you're doing these, what's going to happen is, what I highly recommend you do is you don't think about this right off the bat. Okay, what I want you to do is I want you to think about the EGL, which is all of this, okay, which is equals to all of this. Okay, what is the energy doing as it goes from this point here to this point here? Well, it's decreasing, is it not? It has to, right? It will never go up on its own unless there's a pump, okay? And you can write this down. Unless there's a pump, it's always going to go down. Okay, so here's the EGL. We're going to start, it's somewhere up here. And it's going to go to a point down here, and it's going to basically slowly decrease. Now, why is it decreasing? Friction. Okay, so there's friction in that pipe. And that friction is causing us to lose energy. Okay, so between those 2 points, we have lost some energy. Okay, now maybe we should draw a line for the flat line, so we can kind of say, okay, well, this is, here's the flat line, like this. Okay, and this right here, okay, not very colorful or beautiful, but that's our EGL. Okay, so let's think about some other things. Okay, let's think about these terms in turn. Okay, so let's erase all this, and let's now get back to thinking about our individual terms. Okay, here's Z. Boom, right? We've kind of got Z pretty well knocked out. Okay, so if we're concerned about what's going on in the center of the pipe, or maybe we're not even concerned about the center of the pipe, maybe we're concerned about the side of a pipe, but usually we want the center line. Okay, so there's Z. Okay, what about V squared on 2G? Okay, I haven't told you anything about this system, so it's impossible to know what it is. But we know that it's constant, right? Because if this area here is the same as this area, by conservation of mass and Q being constant, then the velocity has to be the same at, let's say, 1 as it is at 2. Okay, so if the V squared on 2G is constant, that means that here's my V squared on 2G, here's my V squared on 2G. It is the same, and it's going to be the same all along here. Okay, v squared on 2g is going to be the same all the way along here if I could draw. Okay, so that's kind of cool, right? So there's my v squared on 2g. And there is my HGL. Okay, so this is v squared on 2g. And this is v squared on 2g everywhere. V squared on 2g. Okay, the difference between the EGL and the HGL is just v squared on 2g. So once you figure that out, you're good to go. All right, so then that only leaves this pressure head. Okay, well notice the pressure head we can figure out graphically by just saying, well, that's this distance right here. Okay, P on gamma. So then, down to Z, this is P on gamma. Depends on the spot you choose, right? It could be anywhere in there. This is P on gamma. So notice that as we move along this pipe, okay, the Z is remaining constant because the pipe is parallel. The velocity head is constant, so this one is constant. This one is constant. But the pressure is, we're slowly losing pressure as we move down this pipe. Okay, and we're losing energy as a whole. So what do we call this right here? Okay, you may or may not have guessed, this is the head loss, so we're going to put a little HL on it. Okay? So what I recommend when you're drawing these, okay? This is how I recommend you draw them. And we'll come up with some more general rules to help you guys as we go. But one, okay, draw the EGL. Okay? And I'm going to enumerate as we go through this lecture kind of how to draw the EGL, what the EGL means and everything. But basically, okay, it's going to be like a, let's see, so I guess we would say unless there's a pump, okay, EGL will always slope down. Always slope downwards. Okay? And it's going to slope downwards. The slope is going to be steeper when we're losing more energy. So we lose more energy in narrower pipes and in pipes where the velocities are high. Okay? And then you draw the HGL by subtracting v squared on 2g from EGL. Okay? And there's a lot of little sub-rules and just things that you have to think about with this. But what we're going to do is I'm going to go through a handful of examples, and we're going to talk about these. And so what I'm going to do is the way that I would normally, quote-unquote, draw these is basically I'm going to talk about the EGLs first. Once the EGLs are, quote-unquote, drawn, we'll come back and we'll talk about the HDLs and how to figure out what they are. Okay? So let's do this. All right, so let's zoom over here, and I got a whole bunch of these, as you'll see, and we'll kind of talk about them one at a time. Okay, so here we go. We've got the HGL and EGL have already been drawn on these, but I want to talk about how we would know that they are where they are. And so what we're going to do is we're only going to talk about the EGLs first, okay, for the first 6, and these are just examples, and then we'll kind of branch out from there, and we'll talk about some other things, okay? So first of all, I'm going to start right over here, and we're going to look at the EGL from this point right here. Okay, so what is the EGL right there? So I wanted to remind you what the EGL is. Okay, so the EGL equals P on gamma plus Z plus V squared on 2G. Okay, and just as a reminder, the HGL equals the piezometric head. Okay, so it looks like that. Okay, so we're not going to do HGL at first. We're just going to do the EGL. Okay, so we've got a Z here. Okay, so well, let's kind of discuss what's going on in this picture first. Okay, we've got a reservoir up here. Reservoir, so it's got some, water or something in it. The flow is entering this pipe. As it moves down the pipe, let's see, it's cruising, and then it gets down to the bottom, and there is a turbine. Okay, so the turbine is going to remove energy from the flow, and then the flow leaves the turbine into an expanding pipe out into another reservoir. Okay? All right. So let's talk about how we would do this. Okay, so I'm going to do this all in red. And we'll say, okay, well, what is the, so I'm going to look at this first point right up here, and what is the Z? Well, look, we've got a Z that looks like, well, if my hand doesn't slip, it goes all the way down to my datum, wherever my datum is. Okay, so let's call this my datum. Okay, so boom, there you go. Okay, there's my datum. That's Z. Okay, what's the pressure right there? Oh, it's attached to the atmosphere, so the pressure is 0. What's my velocity? Well, it's in a reservoir. The reservoir is really big, so the velocity is 0. Okay, so that is my HGL. So my HGL in this reservoir is going to be right along here at this surface. Okay? Right? Why? Because Z exists and it's huge, and pressure is 0, and V squared on 2G is 0. Okay, so that's where it is. Okay, now what happens, though, as we move along? So we're going to get here, and we're going to start to flow. And as we start to flow, there's actually a head loss right here. There's a head loss that is not accounted for in this drawing. So we're going to just ignore for now. Ignore for now. And I'll show you how to deal with that. There's a head loss as it enters. Anyway, but notice, as we start to flow down this pipe, we're going to lose some energy, right? And every foot we move along that pipe, we're going to lose a little bit of energy. Okay, we're just losing a little bit. Not a ton, but we're losing. And we're losing because we're flowing along, and there's friction in that pipe, okay? So there's a little friction. So what it's doing is it's converting some of that useful energy, which is either elevation or pressure or velocity head, and it's converting it into heat. Okay, so it's converting it to a non-useful. So you can see that as we're cruising along, we're losing, and so that's why this line is sloping downwards. All of a sudden, we get to the end here, and something happens. Well, we've got a turbine. So what happens is the turbine's whole job is to remove the energy of the flow. So what happens is we get an H with a lowercase, I usually use a capital T, and there's a massive energy loss. Okay? Now you might say, well, what kind of energy loss is it? Did we lose velocity head? Did we lose pressure? Did we lose elevation? And we'll talk about that in a second. But right now what's clear is that we lost all this energy to the turbine. Okay? So where it comes out, then we're now in this new pipe. And I want to note that, okay, the slope of the EGL slope, okay, or the absolute magnitude of the EGL slope is going to be largest in narrow pipes, okay? And there's a reason for that, because in a narrow pipe, so EGL slope is, I guess I would say, large when, one, narrow pipe, and that just means that because when it's narrow pipe, the friction from the walls is more important. 2, rough pipe, so if the pipe is made of concrete as opposed to glass. Okay, and then 3, the velocity is high. Okay, so the narrow pipe and the velocity is high often go hand in hand. So what happens is, basically, right here is we're going to lose energy faster, okay, because we have a narrow pipe. Okay, and then the slope of that line is going to level off. So if I zoom way in, which hopefully this will let me do, if I zoom, I don't want to turn the picture. Okay, you can see that I've tried to slope this to make it kind of like concave upwards. Okay, so the slope here, so this is a large slope in an absolute value sense. Okay, and this is a shallow slope right over here. Okay? Now, how did I know that this thing was going to end where it ended, right? Like, I could have drawn it anywhere, and normally you're not going to have, this isn't going to be drawn for you. But what I did is I had it come in right, well, you know what, I'm going to have it drop a little bit right there. Okay, so you see this little drop right here? That's because there's a loss right here due to this exit. Okay, so this right here, that's a head loss due to the expansion. Okay. And then all of a sudden, look, it's another reservoir. And just like the reservoir at the beginning, the only energy we have is this, Z. Okay, because if I look right here, I don't have a P on gamma and I don't have any velocity, because once we get into here, it's really large, so we don't have any velocities. Okay? So that's the first EGL. Okay, now we're going to do a few more of these, so don't fret if that was a little bit complicated. That is a little bit complicated. It is complicated. Okay, so let's see what happens in a pump. Okay, now this pump is a little bit interesting because, the pipes are, continuing, and we just want to look at just what happens in a pipe, in a pump. Okay, so here we go. We're going to analyze these terms. Well, here we go. This is, why are we analyzing terms? Right, we're getting ahead of ourselves. Okay, the EGL is just somewhere above this line. Okay, it looks like they decided, whoever drew this, they drew it up here. Okay, it's sloping downwards. Why is it sloping downwards? Because we're in a pipe and we're flowing. And if we're flowing, we're losing energy due to friction. So we're always sloping downwards. Okay, we're going downwards. Wait, looks like we're going to go up. Why are we going up? The only time we can go up is if we have a pump. So that gives us HP, okay, which is a pump powering the water, giving the fluid more energy. Okay, again, you will ask yourself, well, what kind of energy? Okay, is that pressure? Is that velocity? Typically we want to think that it's going to be velocity. It's logical to think that, the fluid flows into the pump makes it accelerate. Okay, but we'll talk about that when we get around to it. Okay, and then, we're in the same sort of pump. The same sort of pipe, so we're going to lose energy and then we're going to slope downwards. Okay, so here's our EGL. Okay, do not think about that HGL yet. Don't overthink this, okay? EGL, okay? When we're in the pipe, we're sloping downwards. The only time we're going to go upwards is if there's a pump. If there's a turbine, we're going to go down, okay? If there's a head loss, we'll go down. Okay, so let's, let me see, maybe I'll take this one over here, give ourselves a little bit of space. Okay, notice, again, oh, look at this. We have a reservoir. Okay, reservoirs are nice because I know that the only thing I've got here is Z, as they call it Z1. Okay, let's zoom all the way in. There's no reason to be kind of in. Let's get all the way in there. All right, so here we go. So the EGL is at the surface. I'll note that the HGL is as well, but we're not there yet, okay? Then what happens? Well, there's actually a head loss here that we're ignoring. We'll just kind of go with that. And we're going to lose energy. And as we lose energy, we're just going to kind of slope. We're losing energy. Why are we losing energy? Because we're going down a pipe. Okay, now, one of the things that you're going to ask yourself at this point is you might say to yourself, well, how do I know where this line is going to go? Because I might, you might come in here and you might say, well, I want to draw the line here. Or you might want to draw the line here. Or you might get it right and draw it here. How do you know where to draw it? Okay? And the question comes down to you have to know where you're going to end up. Okay? So in this case, I'm actually going to go all the way to the end here. And I'm going to note that at this point right here, the fluid is moving out into the atmosphere. So here's Z. Okay, Z is the elevation of the fluid. And then, let's see, so P on gamma. Well, there is no P on gamma. So we've got P on gamma, Z, and V squared on 2G. Well, there is no P on gamma because this is emptying into the atmosphere. Okay? But there is a V squared on 2G. V squared on 2G. V squared on 2G. So in other words, there was no way for you to know where necessarily to draw this line, but it had to end up above Z. Okay, so this particular option right here, this one is a no-go. Okay, you also couldn't have drawn it to have it go directly to Z. It just had to go above Z some amount. So you could have drawn, so this line, which I'm erasing now, would have been fine. Okay, but I'm going to stick with the one that these people created. Okay? Okay, got a little mixed up there. Anyway, all right, so here we are. So you're cruising along this thing, and you're losing energy. Notice they're measuring their EGL using one of these pitot tubes. Okay, so this is how they're measuring it. Notice that the water, or if the fluid is rising to the exact elevation of the EGL. Okay, we're going to keep going down, and then boom, we hit the end. Okay, so cool. So that's how it works. Okay, notice that all that energy that we lost going, that EGL going, that represents the loss of energy. That is the head loss. Okay, so the total amount of energy we lost due to friction by the end is this much. Okay, and at the beginning, right over here, we hadn't lost any yet. Okay, so that is the head loss. Okay, so that's how we do EGL. Okay, let's see what else we can find here. Oh, this one, I love this one. This is a very confusing one, but I do love it because it's a very thoughtful one. Okay, so don't look at the rest of it just yet, but we'll get there. Okay, so again, there's a head loss right here that is currently being ignored. H lowercase l ignored for now. Okay, so again, we've got a reservoir, which means we're going to start right here. Okay, so we're cruising along. EGL, total energy. Okay, we're ignoring this little head loss, and then what's going to happen? Well, we're going to start to lose energy. Well, we're cruising along this pipe, so we're losing energy. Whole time we're losing energy, right? Because we're in a pipe. Now this pipe is weird because it goes above our energy grade line, so we'll talk about that in a bit. But right now, look, we're just losing energy. It's okay. Now again, how did I know where to end up here? Well, if this is my datum, here's Z. Well, that's a really bad datum. Let's not be that sloppy. Let's erase that. Okay, here's my Z. Here's my Z. It's exiting to the atmosphere, so I know I've got V squared on 2G right here. So I just need to aim somewhere above this point right here. Okay, so when I get there, as far as I'm concerned, when you get there, the line is kind of done. You know, once the flow is just kind of like water flowing through the air. I mean, it's still a fluid, but it's got no pressure, and it's not really going to stay together. So it's hard to really imagine it having a single. Well, it never has a single Z, but I don't even know how to define like the center point or whatever. I mean, I guess you could do a centroid. Anyway, so we're going to keep going. So that's the energy grade line there. Here's another energy grade line, and I love this one as well. I love them all. I'll stop saying that I love them. I'm just a loving person. Okay, can we zoom in and not? Okay, thank you, jerk. All right, so again, look, this one, and this one's interesting because we start out, here's a reservoir. Oh, come on, man. Give me a reservoir. Okay, here we are right up here. Okay, this is the EGL. Okay? Now again, let's not overthink it, right? There's an entrance loss here, which is not accounted for. There's also a contraction loss here, which is not accounted for. Don't ask me why. So we're going to ignore these for now. Ignore for now. Okay, but we're in a pipe. So we're losing it. Well, let's try to figure out where we're going to end up. Okay, so at the end here, we want to end up down here. Okay, so this is where the EGL is at the end. Okay. Now there's a head loss right here. There's energy that is lost due to the exit. And basically, you know, we've been ignoring these, but this is the first one where we're not going to ignore. And that's just because whoever made up these examples didn't ignore it. But what it is there's just a loss of energy because this fluid comes in and it's got all this energy and then it swirls around and does all this stuff and then that energy just kind of dissipates. Okay, and it turns into heat. Okay, so they call that head loss at the outlet, or we could call that HL at the expansion. Okay, is this much. Okay, it's arbitrary. It's not really, I mean, when you're drawing it, it's arbitrary, but it's not arbitrary in real life. Okay, so now, well, that's where we want to end up. So, is we want to end up at this point right here, and we want to have room to lose that energy right here. Okay, so now the last thing is, okay, where am I going to lose energy faster? In this fat pipe or this skinny pipe? Okay, so large pipe or small pipe? And over here, okay, we have a small pipe, so V squared on 2G is going to be higher. Okay, that's going to cause more friction loss. And also, whatever the roughness of this pipe is, it's going to be more important over here. So what happens is we're going to lose energy faster over here. If we lose energy faster, that means we're going to be steeper over here. Okay, steeper loss of energy here than over here. Okay, so it's going to look like this. Okay, so we're not going to lose energy very quickly over here, and then we're going to hit some point, okay, where the pipe starts to contract and we start to lose energy faster. Okay? And the curve in that line is because this doesn't all happen at once, right? If it happened at once, there would be a corner right up in here somewhere, but it happens over, some distance. Okay? So that's the EGL, okay? The energy grade line. Again, it's just all about total energy. It's all about losing energy. Okay? So let's zoom away from that one if this computer will let me. Okay? And let's look at this one. Okay? So this is fluid exiting the pipe into the atmosphere. Okay? We probably should have done this one earlier. Anyway, so we got fluid coming. This is unbelievable. Okay, we got fluid coming through this pipe, exits the pipe right there. Okay, so as we're coming down the pipe, okay, again, the only key here is where do we want this thing to end up? Well, we just need to make sure that we're above this thing somewhere. Okay, whoever drew this one decided that was going to be right here. Okay. Okay, and it has to be above that one because we've still got a velocity head right there. Okay, so we're going to keep cruising along, and then we're going to get to this point right here. Okay, noting that we've got v squared on 2g right here. We've got z going down to a datum down here. Okay, and we've got no pressure right there. Okay, so that's how we do it. All right, so that's how we do the EGLs. Okay, and that is all there is to the EGLs. Okay, so let's zoom out here. I'm going to grab this one, which I like and we'll do later. And I'm going to grab this one, which I like and we'll do later. And I'm going to put them down here. Okay, and let's zoom. Let's see here. Where should we go? I don't remember which one of these we did at first. Oh, it looks like I'm covering all my notes. Anyway. Yeah, let's do this one. Okay. The HGL. How do we get the HGL? All right, so we'll do this one in blue. Okay, HGL. Okay. Once you have the EGL, it equals the EGL minus v squared on 2g. Okay? That's it. Okay? So what we do here is we're going to go in here and we're going to say, okay, well, let's do the HGL. All right, so notice this pipe has a constant diameter. All along here is constant diameter. If it has a constant diameter and the flow rate's the same everywhere, well then v squared on 2g is the same everywhere. From here to the turbine. Okay, so that means that I can draw my HGL just being some distance below that EGL, and that distance needs to stay constant. Okay, why? Because v squared on 2g is constant. Because area is constant. The area of the pipe is constant. Okay? That's not the case over here, though. Okay, so we're going to have to zoom in down there and consider what's going on here. Oh, that's how it got to be so big. Okay, I see. Whatever. All right. Fun with teaching. All right, so what we note here is that the v squared on 2g over here, note v squared on 2g right here is going to be a lot higher than it is right here. Okay, now why is that? Okay, why is the velocity higher next to the turbine? Well, because the cross-sectional area is smaller. Okay, so we can go down here and I can note that the the v squared on 2g is increasing. Excuse me, the v squared on 2g is decreasing, which means this distance between these two is decreasing. Okay, so they're going to get closer and closer and closer together. Okay, until they meet up. Okay, and they're doing that because the velocity is decreasing, because the velocity is going to 0. Okay, and then there's a little head loss right there, and then they're all joined up right here. Okay. Oh, so I should also note that there's no velocity inside the reservoirs, so the what do you call this? The HGL and the EGL are on top of each other. Okay, at reservoirs. Okay. Okay. Notice that little downward tick right there. Okay, so if we zoom in right there, notice this little downward tick. Okay, and what that represents is basically over here somewhere, right? We had pressure and we had elevation, which is going to go from this end, P on gamma and Z. Now, Z's going to go all the way down. Okay, as we approach here, all of a sudden, some of that pressure is going to be converted into velocity, v squared on 2g. Okay, all of a sudden, we're going to have motion. Okay, and where did that motion come from? Well, it came from the pressure. Okay, so note, on this particular problem, as we're moving along, we're losing elevation as we go down. Okay, and the pressure is increasing though. And why is the pressure increasing? Well, the pressure is increasing at the expense of the elevation, right? Because the velocity is constant. The v squared on 2g is constant. And we're just gaining pressure, gaining pressure, gaining pressure. And then all of a sudden, here's this turbine, and the turbine takes all of that pressure and basically removes it. Okay? And this is how a dam works. Okay, or hydroelectric power. That's how it works. Okay, you put it at the bottom of the dam because you want to get as much of that pressure head as you can possibly get. Okay? All right, so let's, well, you're getting a little bit wonky here. Let's zoom in. All right, let's do this pump. All right, so note, okay, what's my area of my pipe look like? Looks pretty constant, doesn't it? Okay, so what does that mean? Well, that means the v squared on 2g. So again, I'm going to take my EGL and I'm going to subtract v squared on 2g. V squared on 2g in this case is constant. Okay, so it's going to be a constant distance all along here to there and all along here going that way. Okay, v squared on 2g is constant. Okay, constant, constant, constant. So what does that mean? Well, let's at this point, it's pretty easy to kind of get a qualitative sense of what my things are. Okay, so here's my Z. Here's my P on gamma. And then here's my V squared on 2G. So note that with the pump, when the pump happens, okay, we're losing pressure, losing pressure, losing pressure, losing pressure, and the pump comes and we get a whole bunch more pressure. Okay, so what the pump does is it pressurizes your flow. It cannot cause an increase in V squared on 2G, and the reason for that is because if it did, it would be violating the law of conservation of mass, right? Whatever flows in has to flow out. It can't all of a sudden create more fluid to flow out, right? So the other thing to note is that by the pressure being higher here than it is here, than it is here, than it is here, that's what's driving the fluid to flow in this direction. Okay, is it's flowing from high pressure to low pressure. Okay, if there was no pressure gradient, there would be no flow. Okay, something to think about, unless it just had momentum, in which case it would be slowing down. Okay, all right, so let's see. I seem to have lost a few of these. I don't know where they went. It's very interesting. Okay. Let's go down here. Okay. So we've got a, let's see. So again, we already have the EGL. So to get the HGL, all we need to do is subtract V squared on 2G. So we're going to come in here, we're going to look at it, and we're going to say, oh, look, okay, is the pipe changing in cross-sectional area? It appears not to be, right? I mean, usually on a test, I'll have to tell you, or it'll have to be very clear whether or not the cross-sectional area is changing. But in this case, it's the same everywhere, right? So let's go ahead and let's draw in blue the HGL, which is going to, okay, follow. It's always, so there's no velocity, no velocity, no velocity. All of a sudden, we've got velocity. So now the velocity is going to be always the same distance below the EGL. Okay. Now, how do I know where it's going to end up? Well, it has to end up right there. And why? It has to end up right there because the HGL is Z plus P over gamma. Well, there is no P on gamma right here because we're entering the atmosphere. So P on gamma is 0. So that's what it has to be. Okay? So note, now this is where it gets a little bit fun, right? So our Z, okay, is, let's see if we can draw this in black. So our Z is right here. Okay, note, so here's Z right here to the middle of this pipe. Okay, now here in blue. Then that means this is P on gamma, right here. And this is V squared on 2G. But something special happens. So notice V squared on 2G is constant through the whole thing. And V squared on 2G, of course, cannot go negative. Okay, but notice all of a sudden, so here's our Z. So Z's going to this line right through the middle here. Okay, so remember that the HGL equals P on gamma plus Z. Okay, so that's that blue line. Okay, so for example, right here, here's Z. Now, if we have to add to get, if we have to, Z, we have to add P on gamma to get to the HGL. We're adding a negative. So that means we're at negative pressure here. Okay, so from about this point, more or less, to about this point right here. Okay, so everywhere in here, we have a negative pressure. Negative P on gamma. So what does that mean? Well, I'll tell you, it means a few things. It means that if I look at the pipe in that area, so here's my pipe in that area, if the pressure in here is negative, then what that means is that the pressure out here is 0, right? Okay, because this is all gauge. Okay, remember this is all gauge. So what that really means, so let's see, this is the pipe. Okay, the other way to think of it is pressure, let's say 14.7 psi, pressure less than 14.7 psi. Okay, so this is atmospheric and this is below atmospheric. Okay, so what you need to worry about in these situations, when you see negative pressure, you want to check for cavitation. Okay, by comparing the pressure to the vapor pressure of the fluid at that temperature. And the other thing is, you just want to remember that because the pressure on the outside is greater than the pressure inside, the pipe could collapse if it's not strong enough. Okay, usually the pressure, the water, the fluid in the pipe is a higher pressure than the fluid outside the pipe. So that's usually not an issue. Okay, so just food for thought. Okay, so anyway. Let's zoom in. Okay, this is the most important example that we are left to do. So let's zoom in here. Okay. Okay, HGL and EGL. Okay, again, remember, if we want the HGL and we already have the EGL, what we're going to do is you're going to draw right through the middle, okay, while you're on the reservoir. Same thing over here on the reservoir. Okay? We don't worry about head losses when it comes to the HGL. Okay, so all this business with the head loss of the outlet, don't worry about that. All we need to do is figure out what the V squared on 2G is. Okay, so the V squared on 2G here versus the V squared on 2G here. Where is the V squared on 2G highest? Well, in a small area pipe, we're going to have V squared on 2G is going to be the highest. Okay, so that means that this distance right here is going to be larger than this distance right here. Okay, so that's all we got to do. Okay, so we have all of a sudden we have velocity, so some of that pressure is going to be changed into velocity. Boom, cruising along. V squared on 2G is pretty small. Okay, and then we get right in here, and then over here, note V squared on 2G. Okay, boom, we're doing great, right? It's pretty big though, right? And then we get up into this region, and there's some kind of transition here, okay? And they kind of draw it, I think they draw it kind of as an S-curve, which I think I'd have to really think about. I guess it depends on how it's closing. But an S-curve is very good. Okay, we'll take the S-curve. I'm not really too worried about you figuring that out. Okay, so that's how we do it. Okay? Now, we're going to do one of these from scratch. and or two of these from scratch. And I don't know it. Let's zoom out and let's, come on, man. Let's make sure that I haven't lost anything along here. Okay, so we've got these two. I don't see anything lost underneath it. These two. I really thought I had more than that. I wonder if I accidentally deleted something. Interesting. Okay, so let's go down here and let's do these two from scratch. And that'll be it for this rather long lecture. All right, so here we go. Okay, first of all, what I'm going to do here is I want to note where there are head losses. Okay, so there's a head loss. Let's zoom in a little bit more. Okay, so there's a head loss right here. I usually like to circle them. Okay, there's an entrance, so there's a head loss. There's an exit, so there's a head loss. Okay, what does that mean? Well, it means that there's going to be a sharp loss of energy in the system right there. Okay, so here's my EGL. Okay, so I'm going to start at the surface of the reservoir because I have Z, but I have no pressure, I have no velocity. Now, sometimes what you'll see is some people will start, well, it doesn't matter. We're going to go right here, and then we're going to lose energy at that exit. Okay, so right here, I'm going to say this is a head loss at the exit. Okay, so that's H lowercase l at the exit. Okay, now what? Well, now I'm going to lose energy approaching from one side to the other, but notice the pipe is not at a constant diameter. So this is going to be a little bit tricky. Okay, so I'm going to go down here, and we're going to work backwards a little bit. So this is my EGL. Okay, notice there's a head loss right there, so there's going to be a little bit of, that's going to be the head loss to the exit. Okay? Now, where are we going to be losing energy the fastest? So where's the slope of this line going to be? So I know that I need to draw a line from this point to this point, but I need to know where is the energy lost the greatest, okay? In the narrow pipe or in the fat pipe, okay? And hopefully what you can think about is you can think that over here, v squared on 2g will be small. Okay, and it is because v squared on 2g is small that we're not going to lose energy very quickly. Okay, so it's going to be relatively flat, and then what's going to happen is we're going to lose energy more as we come this way. So it's going to be concave downwards. Okay, so it's going to go downwards like, as best I can draw it, which is not very good. But concave downwards. Yes, you have to get the concavity correct. Okay? Okay, now we want to get the HGL. And all we want to do is we just want to think about v squared on 2g. Okay, because we know we're going to be right here. We know we're going to be right here. Okay, but I want v squared on 2g. Okay, so we're going to be below the EGL by v squared on 2g. So where is v squared on 2g the largest? Well, v squared on 2g is the largest over here. Okay, it is the smallest over here. So in other words, we're going to be very close to the line over here, and as we go this way, we're going to get farther and farther and farther away from that point. Now we know we want to end up right here, so it's going to be like this. Okay, it's going to be even more concave. Okay. So v squared on 2g is getting larger. Okay, so that's v squared on 2g. Okay. Now, if I ever asked you to label everything, then you would come in here and you would say, okay, well, here's the datum. And you would say, okay, well, here's Z. You would say, well, if we want to keep with our color coding, this will be P on gamma. And this will be v squared on 2g. Okay, and obviously I drew this in the wrong color. I'm not sure if that really matters. V squared on 2g. Okay? And that's how we kind of do these. Okay? And let's see, I'm going to draw a bigger, more complicated one over here. Okay, and you can see this one's got all kinds of noise. All kinds of noise. Okay, now what's nice about this one is it's got a pump. So pumps allow a lot of freedom with drawing. So I always love it when I see a pump on one of these. And I'm going to pull out a ruler here so that I can work this one. It looks like we got about 5 minutes till the hour. So let's see what we can do here. Okay, so we're going to start with the energy grade line. Okay, so let's see here. We're going to start here. And we're going to finish here. Okay, they're going to be energy losses. Anywhere something changes. Okay, there's a loss here. There's technically a loss here, but we're probably going to ignore that because it's really hard to draw. Here, here, here. Okay, so we're going to ignore that one right there because it's just really annoying. Okay, we also have this pump that we have to take into account, which is going to cause a major increase in energy. Okay, granted, this is all qualitative, so you can draw it however you want. So what I'm going to do is we're going to lose some energy right here. Okay, so that's going to be the head loss due to the entrance. Okay, now we have to think about these pipe widths. So this is the smallest, I'm going to go ahead and say. I'm going to say this is the smallest. Let's see, this is the second smallest. This is the second largest. It'll be the same in both of these places. Second largest. And this will be the absolute largest, okay? So why am I thinking about that? Because I'm thinking about the slope of my line, right? So the largest pipe is going to have v squared on 2g is going to be the smallest, right? The second largest is going to have v squared on 2g is the second smallest. The second smallest pipe is going to have v squared on 2g. It's pretty big, okay? And then the absolute smallest is going to have v squared on 2g, double big. Okay, or whatever. So anyway, so with the second largest, that means that the slope here is going to be relatively gentle. So I can kind of draw it like, I don't know, like this maybe. Okay, now it hits a pump. So what happens when it hits the pump? Well, we're going to gain all kinds of energy, right? So we're just going to like shoot up. Now you might say, well, how high? Well, I don't know. So I don't really want to, the nice thing is you have kind of a little bit of artistic freedom here on this one. I'm not going to like play with that too much. I'm just going to go over here and I'm going to work from the other side because that'll kind of tell me how high I want it. It's just going to be wherever I end up, okay? So like right here, we've got a head loss, HL due to the exit, okay? Now, as I work backwards, I need to think about this slope here, okay? V squared on 2g is pretty big here. So maybe it's going to look like, it's got to be steeper than that one over there. So maybe it's like this. Okay. Now we've got another head loss here. So I'm going to do, I don't know what that head loss is. Again, this is all qualitative. So I'll call this, so why do I keep writing L's? HL, I'll call that entrance because it's going into a smaller pipe. You call it whatever you want. All right. Now we're in a really, really large pipe, so the slope is going to be very gentle because v squared on 2g is very little. Okay, so we have very low velocities, so we're going to have a low slope there. Okay, again, we're going to have another head loss there. Head loss due to, I don't know, expansion there. Okay, so now we're in this smallest pipe working backwards. So we're going to lose energy very quickly. Okay, so this has to be the steepest line because we're in the smallest pipe. Okay, till we're somewhere even with this contraction, which I'm not going to really deal with the losses there. But now we can kind of start to, I know that the slope here is equal to the slope here. So we can kind of do like this. And then it looks like it's going to hit that thing and it's going to kind of curve into it like so. Okay, so there it is. So this is the HP. Everything is labeled, okay? Now, why are we sloping down? Because we're moving through pipes and we're losing energy due to friction, okay? Now, let's do the HGL. Okay, so we're cruising along. Okay, and then all we need to think about is, oh wait, I wanted to make a point that these two have the same slope. Right here and right here have the same slope. Okay, so we're cruising along now. Only want to think about v squared on 2g. Okay, I want to note that we're going to end up right here. Okay, so V squared on 2G right here, we know it looks going to be like this. Okay, coming from the back end. Okay, so that is the second largest V squared on 2G. Okay, this is the smallest V squared on 2G. So that one's going to be like this. Let's just make it really tiny. Be in there. Okay, really close. Okay, this one is the, it's got V squared on 2G is the biggest. Okay, so maybe we can exaggerate that if you want to. Right, we're going to go from about here to about there. V squared on 2G. Okay, ideally parallel in this case because the pipe is parallel. All right, and then right in here, where it says second largest, we got V squared on 2G is relatively small. Okay, so we're gonna kind of be like, I don't know, somewhere maybe like this. Okay. All right, so now we just need to connect the dots. Okay, so this is gonna look like that. This is going to look like this. That's right. It's got some funny shapes. Okay. And there it is. Okay. And if I were to ask you to label this, we would come in here and we would create a datum. Okay. These would be my Zs. My Z is basically to this line right here. You know, that line right through there. That's if we're doing the center line, which usually you are. So that's Z. Okay, the pressure is from that line to the blue line. Okay, so, you know, that's the pressure. Okay, noting it's usually the thing that's getting messed with the most. Notice from either side of that pump, notice the pump increases the pressure tremendously. Okay, the V squared on 2G, that's this stuff right here in red, V squared on 2G. Very hard to draw right in there, but it's in there. Okay, and that's it. Okay. Now notice, some of these things are pretty weird, right? So like if I zoom in right here, for example, this is really weird. Give me something to write with. If I zoom in right here, that's pretty weird. What's going on right there? Okay, what's going on here is basically as the fluid is moving through this pipe, all of a sudden, okay, it's decelerating greatly. So we lose all of this velocity head, okay, disappears because it decelerates. Okay, so now we've got almost no velocity head. And where did that energy go? Well, now we're in a much more pressurized, this is much higher pressure than we had back here. Okay, and so the velocity head gets converted into pressure. Okay, and then that pressure gets turned back into velocity. Okay, and that's the law of conservation of energy. Okay, so anyway, that was a rather long lesson. That's 18A, so there will be a B. And B, we're just going to work two problems. Hopefully it won't be too painful or too long. All right, I'll talk to you later. Okay, I hope you're having a good one. All right, bye. Why?